Hello students, I hope, am I audible? Hello students, I hope. So guys, we are starting with control system and the topic is introduction to frequency domain analysis. Okay, so let's begin with this. So guys, to begin with this, let me know if I'm audible. I hope you are watching this lecture. आज का टॉपिक है frequency domain analysis. Let me know guys if I'm audible. In fact, we are not going to get into a very detailed stuff of frequency domain. In fact, we are just going to see introduction to frequency domain analysis. So my question to all of you is, what is the requirement of having a frequency domain analysis? Can anybody tell me what is the requirement of having a frequency domain analysis, guys? Come on, tell me, guys. So I'm waiting for this. If you tell me what is the requirement of frequency domain analysis, it will give me an idea कि आप लोग को कितना ऑलरेडी पता है फ्रीक्वेंसी डोमेन अप्रोच के बारे में और फ्रीक्वेंसी डोमेन इतना इंपॉर्टेंट क्यों है, क्या मायने रखता है फ्रीक्वेंसी डोमेन एनालिसिस. ओके, ऐसी कौन सी चीजें हैं जो आसान हो जाती है फ्रीक्वेंसी डोमेन एनालिसिस में, या फिर फ्रीक्वेंसी डोमेन एनालिसिस में ऐसा क्या होता है जो टाइम डोमेन एनालिसिस में नहीं हो सकता. डेफिनेटली टाइम डोमेन एनालिसिस और फ्रीक्वेंसी डोमेन एनालिसिस ये दो टाइप के एनालिसिस है टू for analyze the system's performance, isn't it? So when to prefer time domain analysis, when to prefer a frequency domain analysis? I hope you got my question, guys. Okay, so tell me, Deepak, what is the necessity of having a frequency domain analysis? Why can't we go for time domain analysis every time? What is the necessity that you need to get down to a frequency domain analysis? You can answer me in English, Deepak. Come on, Deepak. What's the necessity for getting signals? Oh, okay. That's not the reason why we go to frequency domain. So I'll tell you the possibilities where I have to go for frequency domain. Okay, let's see. The first example I'll tell you. I hope you are aware of such signal which I'm drawing now. Okay, let me know what type of signal it is. Of course, on x-axis we have time, on y-axis let's say we have some voltage. Okay, can anybody tell me what type of waveform is this and where you have seen this waveform? Come on guys, I'm sure you can answer me this question. It's a very simple question I have asked. Somewhere or the other you must have seen such kind of waveform, and in case if you have seen this waveform, I would like to know where you have seen this waveform, in which subject, or it is related to which topic. It's a very well-known signal, guys. It's a very well-known signal, guys. Can anybody tell me what kind of signal is that? Okay. Okay, in power system you have seen. Let me tell you guys, such signal is called as an amplitude modulated wave. Okay, such signal is known as amplitude modulated wave. See, like we have in our music system as AM and FM. I hope you know that AM and FM. Out of which this is what we call as AM signal, that is amplitude modulated wave. I hope you understood that. Okay. So since this amplitude modulated wave, guys, you know, it is plotted with respect to time. Check it out. T stands for what? Time here. So since I can see my AM wave with respect to time, then such signal is said to be in which domain? This AM wave is in which domain? Then we say it is in time domain. Then we say it is in time domain. Okay. So if you want to plot AM signal, of course, there has to be a time domain. Only on time domain only I can see my AM waveform. That is amplitude modulated waveform. Now let me come to the point. My point is, let's say if someone asks you, what is the bandwidth of this? I repeat, if someone asks you, what is the bandwidth of this? What is meant by bandwidth, guys? What is meant by bandwidth? Listen to me carefully. Bandwidth means the range of frequency over which the information is available. I repeat, bandwidth means the range of frequency over which the information is available. That is what we call as bandwidth, guys. That is what we call as bandwidth. So what do I mean by that? Suppose if I want to know what bandwidth. I want to know what bandwidth of what? AM wave. That is amplitude modulated wave. It means this time on x-axis there has to be a frequency. On x-axis there has to be a frequency, so that I'll come to know from where to where my information is present. Let us assume this frequency is f1. Let us assume this frequency is f2. So what do I mean by that? If I actually transform this time domain signal to something called as a frequency domain signal. The reason I'm saying this is a frequency domain signal, guys, because on x-axis we have a frequency. Therefore, such signals are referred to as a frequency domain signal. And now you can see clearly that this signal is existing from f1 to f2. And then that range of frequency is known as bandwidth, because bandwidth is defined as the range of frequency over which the information is available. See, now this is something that you have seen graphically, guys. If I want to see a mathematical expression, then mathematically I can write bandwidth equal to what? F2 minus F1, because this is the range of frequency over which the information is available. And since the unit of frequency is in hertz, so I can write it in terms of hertz. So moral of the story, suppose you have a time domain information, and if someone asks you what is a bandwidth, then there is no answer in time domain. So answer to this question is given only in frequency domain. So what we need to do is we need to transform. Listen to me very carefully, guys. We need to transform time domain signals to frequency domain signal. And for that, guys, you have numerous tools, right? You have a Laplace transformation, you have a Fourier transformation, you have a Z transformation. So if you see all those transformation, what they do, they basically transfer your time domain signal to frequency domain signal. So frequency domain, guys, is very, very important. Frequency domain is very, very important. Can anybody here tell me what is the extra advantage that you get in frequency domain? See, the first thing that I have told you, that if you want to calculate a bandwidth and if you have a time domain signal, you cannot calculate. Then boss, you have to calculate, you have to transfer the signal from time domain to frequency domain. And thereafter only you can get something called as a bandwidth. This is the first reason I have given. Is there someone who can tell me what is the second reason? Why do we go to frequency domain analysis? Come on, guys. Nayan, Deepak, can you answer me? What is the second? What could be the second reason? So let us discuss second reason, guys. Let us discuss second reason, okay? See, the second reason is, suppose you have an LTI system. Hello, everyone. Let us assume this is some LTI system, guys. You have some input here. You have some output here, okay? So you have some input, you have some output. And let's say if you want to know a transfer function, guys, if you want to know a transfer function, let us assume for this LTI system, transfer function is not known. Can anybody help me how to get the transfer function for this LTI system if the transfer function is not known? I'm sure you remember the places, like we have input at this place, we have output at this place, and here we write something called as a transfer function inside the block. So can anybody tell me what is the procedure to know the transfer function if input and output is known to me? Come on, guys. If input and output is known to me, is there a way that you can get a transfer function? And if there is a way, let me know, guys, what is the way to get the transfer function? Come on, guys. Let's make this session interactive, okay? Come on, guys. Tell me. If the input is known to me, if output is known to me, assume that the transfer function is not known to me. Because see, I'm giving you the motivation why we should go for frequency domain analysis. Okay. In fact, this is one of the motivation why do we go for frequency domain analysis. So here in this example, you will understand, with this concept, you will understand better why we must go for frequency domain analysis, guys. Okay. Look at this. Look at this. It's a very nice concept I'm going to explain you guys. Okay. It is very simple. It is very simple. Okay. What they do, if you want a transfer function, you know that a transfer function is a ratio of Laplace transform of output upon Laplace transform of input. Very simple. So let's say if output is known to me, get the Laplace transform of output. If the input is known to you, no problem, get the Laplace transform of input. Then Laplace transform of output upon Laplace transform of input gives you what? Come on, guys, it gives you transfer function. Am I right? So transfer function, in a way I can write, it is ratio of Laplace transform of output whole divided by Laplace transform of input. So this is the way we find a transfer function. But still I didn't tell you what is the motivation that we go for a frequency domain analysis. So here comes the motivation. Listen to me. Let me tell you, this is something, which you can do only on paper. This is something that you can do only on paper. In reality, it is not possible to find transfer function for practical systems, for in fact, practical LTI system. So let's see what happens in practical LTI system. So let us assume this is a practical LTI system. To which, let's say if I applied my input as a step input. Okay. Is it possible in real time to apply a step input? Come on, guys. Is it really possible to apply a step input in reality? Can you answer me in yes or no? Come on, guys. Is it possible to apply a unit step input in reality to an LTI system? Can anybody tell me? You know that unit step input is something which is 0 at left hand side, which is 1 at right hand side, isn't it? So is it really possible to apply such step input in reality? Let us assume this LTI system, it's some electrical circuit. So if this is electrical circuit, it is possible to apply input as a unit step input by applying, okay, by applying 1 volt as a DC supply. 1 volt as a DC supply. Okay. So if it is 1 volt DC supply, guys, if it is 1 volt DC supply, it can simulate very easily as what? As it can, simulate a unit step input only. Okay. So what LTI stands for? It is linear time invariant system. Yes or no? Now, linear system, when I say linear system, guys, L stands for what? Linear. So linear system is that system which satisfies superposition theorem. Okay, I'm sure you know what is the superposition theorem. So the system which satisfies superposition theorem is a linear system. Secondly, what is meant by TI? Come on, TI stands for time invariant. So this is called as time invariant system. So what is meant by time invariant system? Let us assume some transformer. Let us assume some ideal transformer. Now, if at primary, if you apply some input, at secondary, you get some output. I repeat, at primary, you have applied some input. At secondary, you get some output because of the transformer action. Let us assume you have applied the input at, let's say, 10 a.m. I mean, 10 in the morning, you applied the input and you got the output. Okay, this is one step. Second step, you took that same transformer and now you are applying input at 11 o'clock. Then again, you will get the output at 11 o'clock only. Moral of the story, if you give the input at 10 a.m., you get the output at 10 a.m. If you give input at 11 a.m., then you get output at 11 a.m. only. Moral of the story, with respect to time, behavior of the transformer is not going to change. And secondly, there would be nothing called as delay. There is nothing called as delay. That is, if you apply input at 10 a.m., then you are not getting output at 10:05 a.m. You are getting output exactly at 10 a.m. only. So the instant at which you apply the input, at the same instant you will get the output. Such systems are called as time invariant system. I hope the concept of time invariant as well as the linear system is clear to you. So a system which satisfies superposition theorem along with the time invariancy property is referred to as LTI system, that is linear and time invariant system. I hope, Deepak, you are clear with something called as LTI system. Let me know, Deepak, if you have understood what is meant by LTI system. If you have some questions on LTI system, you can definitely ask me. And till then, I'll just move ahead. So what I was saying that, let us assume this is some practical LTI system. So this input is practically possible. As I said, you can apply some DC input and you can simulate what a unit step input. But in reality, output may not be something which what we have seen waveforms like sine wave, cos wave, you know. But for example, if you are getting some output like this, now listen to me very carefully, guys. This is something important, guys. Okay, look at this. If this is the thing, okay, this is the output. Now, you know what? Suppose if I want to still get the transfer function, guys, you got only one formula. That is what? Laplace of output upon Laplace of input. Isn't it? Laplace of output upon Laplace of input. But for example, guys, when I say input as unit step, I know how to take a Laplace of this because I know that Laplace transform of 1 is 1 by s. So this is easy for me to get the Laplace transform. The question is how to get Laplace transform of output. Is it really possible to get Laplace transform of output here? Come on, guys, can you answer me in yes or no? Is it possible to get the Laplace transform of this output? Let me know. Is it practically possible to get Laplace transform of such output? Because in reality, you will get such signals only. In reality, you will never get sine wave. So let me know, guys, if is it really possible or is it feasible to get the Laplace transform of such signal? Okay, Deepak, I would like to disappoint you. Okay, it is wrong answer. Why you cannot do that? I'll tell you. See, you have a Laplace transform of sine signal. You have a Laplace transform of cos signal. You have a Laplace transform of, let's say, t raised to n as n factorial upon s raised to n plus 1. Meaning that to get a Laplace transform, you should have some mathematical expression. I repeat, Deepak, to get the Laplace transform, you must have some mathematical expression. Unfortunately, this doesn't have any mathematical expression. Try to understand my problem. This doesn't have mathematical expression. Okay, so since it doesn't have a mathematical expression, it is not practically possible to take a Laplace transform. How do you take? How would you even take the Laplace transform of this? There is no such mathematical expression, isn't it? And that's the reason why here it comes a limitation. Here I cannot get the Laplace transform of output, guys. I'm able to get Laplace transform of input for sure, but Laplace transform of output is not possible. And let me tell you, if the denominator is known and the Laplace transform of output is not possible, if it's a question mark for me, again, I cannot calculate transfer function. So transfer function you can calculate, guys, if the Laplace of output upon Laplace of input is known to you. I hope you understood that. So this is the problem, guys. This is the problem, and we need to get some solution over it. Okay. So how we are going to have a solution on this. Okay, listen to me very carefully. So what we do, we have some random signal, guys. We have some random signal. So what we can do is we can actually send it to something called as a Fourier series tool. I can send it to what? Fourier series tool. So what is a Fourier series tool, guys? Fourier series tool is a tool which converts non-sinusoidal signals into sinusoidal signal. I repeat, Fourier series is a tool which converts non-sinusoidal signals to what? Sinusoidal signals. I hope you know that. Whether you give a triangular wave or you give a square wave, you know, if you give it to Fourier series, it is possible to get what? A sinusoidal output. For example, let me say some traditional signal. Let's say we have this kind of signal, guys. We have this kind of signal. Okay, so what Fourier series does, whatever signal you have given like this, okay, it is going to convert it into what? Sinusoids. Multiple sinusoids means what? One sinusoid you will get like this, okay, means with the same frequency. The another sinusoid you will see like this, and such many sinusoids you will get, guys. Such many sinusoids you will get. For example, you may have some sinusoidal like this. As you can see, there are infinite number of sinusoids. There are infinite number of sinusoids to which if you add them up, you will get what? You will get square wave only. You will get square wave only. So what does that mean, guys? What does that mean? Suppose if you have input to Fourier series as what? A non-sinusoidal, it can be converted into what wave? Come on, guys, a sinusoidal wave. And let me tell you, if you have a sinusoidal wave, then it is possible to take a Laplace transform. Yes or no? Okay. Of course, when I say sinusoidal, it is always analog. Okay, it is always analog. A sinusoidal wave cannot be digital. Okay, because digital means what? Digital means there are number of amplitude should be fixed. For example, if I talk about a sinusoidal signal, let us assume the maximum amplitude is 5 and let's say minimum amplitude is -5. Then if you count the number of amplitudes lying between -5 to 5, there are infinite amplitudes. So when I say a signal with infinite amplitudes, it is always analog signal. But suppose if you draw such square wave, for example, with amplitude as 5 and minimum as -5, as you can see, there are only two amplitudes in this, +5 and -5. Such signal you can refer to as a digital signal. Okay, so I hope, Deepak, you got the difference, okay, between the analog signal and the digital signal. Okay, so in digital signal there has to be limited number of amplitudes. In analog signal there are infinite number of amplitudes covered. Okay, great. So let me just rub this to avoid any confusion. So what I meant to say, a signal which is a non-sinusoid, to which the Laplace transform I cannot calculate, I can convert it into multiple sinusoids by using a Fourier series tool, and at the end now I can take a Laplace transform. Congratulations. Now you got the Laplace transform of what? You got a Laplace transform of input which was 9 sinusoidal. Once you get that, you will get Laplace transform of output. Once you have a Laplace transform of input, Laplace transform of input was already known to me. So now I can easily get my transfer function. So I hope you understood the thing. Try to understand. Okay. At input of Fourier series tool, it is always time domain, guys. It is always a time domain. But at output of Fourier series, it is always a frequency domain. So again, you had to convert, guys. You had to convert time domain to frequency domain. So it is essential, guys. It is essential, okay, that you should go for from time domain to frequency domain, okay, as and when it is required. Deepak, see, when you are saying if you want to convert analog to digital, so first of all, try to understand you need to have something called as ADC, that is analog to digital converter. Okay, and let me just clear your fundamental first. What ADC does, it converts analog to digital. Ultimately, what it does, I'll tell you. It doesn't actually convert analog to digital. In reality, I'll tell you, ADC is something which converts voltage to data which is in the form of 10101 like that, and voltage is something 1 volt, 2 volt, 3 volt. Please try to understand. People have got misconception that analog is something which is changing with respect to time. No, analog is something in reality referred to as voltage, and digital is something which is a binary combination of ones and zeros which you can actually store into memories, semiconductor memories. This is what analog to digital conversion, guys. And same happens inverse with DAC. So what happens in DAC? You give a digital data, so you give input as data, but the output is voltage, guys. But the output is voltage. Okay, so this is what in reality the analog to digital conversion and digital to analog conversion. So please remember that. Okay, just remove your complete confusions like analog it's something which is changing with respect to time. It's not like that. Okay, analog it's something where you are going to deal with multiple amplitudes, or in fact I would say infinite number of possible amplitudes, because a voltage can be 2 volt, a voltage can be 3 volt also, and between 2 to 3 there are infinite possibilities of a voltage, and that's the reason why input is called as an analog input. But when I say data, there is a fixed combinations, there are fixed combinations, guys, right? So when I say fixed combinations, as in let's say if this ADC is 3 bit, the minimum data possible is 000, the maximum data possible is 111, so you got only 8 possible combinations. So in digital, you can actually count the number of possible combinations. But in case of analog, you cannot count the number of possible combinations. I hope you got that, Deepak. Okay. So somehow we have actually, changed our track of discussion. Very good. Very good, Deepak. So I guess we should move ahead. So I hope you got the enough motivation why we should really go from time domain to frequency domain. So for example, let's say we have some LTI system again. Let's say we have some LTI system to which the input is something called as a sinusoid. Please remember, when the input is a sinusoid input, okay, what is a sinusoid input? Let us assume some a sine of omega t plus theta, for example. Okay, this is just an example. We are taking this. We have to see what is the output. We have to see what is the output. Okay, then what is the output? Okay, then output goes like this. Output goes like this. Remember, output becomes like this. A is something which was already there, multiplied by M, because of course when you are transferring your input, through some LTS system. That system is definitely going to operate on that signal, and when you operate on such signal, the signal is going to get modified. Therefore, previously amplitude was what? It was A. Now new amplitude becomes what? A into M. Okay, so what is M? I'll tell you, need not to worry. Then sine. Remember, that's the specialty of LTI. If the input is sinusoidal, output is also sinusoidal. Please remember that. For LTI system, if the input is sinusoidal, output is also sinusoidal. If input is having frequency as omega, output frequency remains same. It is not going to change, guys. It is not going to change. So what it really changes? It changes only two factors, guys. First, amplitude. And second, phase. So the new phase will be phi. Let's say the new phase is phi. So what is affected, guys? This is what? A new amplitude. And what this phi means? What? A new phase. This is a new phase. Okay. So this A is what? It was old amplitude. And this theta is what? It was old phase. So I hope you understood that. In LTI system, what happens when you apply input as a sinusoidal input, then the new amplitude is A multiplied by M, and the new phase is phi if the let's say previous phase was theta. So we will solve some numerical on this, and then only this will be getting cleared. But please remember, guys, please remember, if this is omega, the output frequency has to be omega only. Frequency never changes. Frequency never changes. Sinusoidal input, sinusoidal output with the same frequency. Only amplitude of the sinusoidal wave may change and phase may change. Okay, rest frequency remains same. Sinusoidal behavior remains same. I hope you understood this. So let me tell you, for frequency domain, we have two options, guys. We have two options. One, Laplace. The other one is a Fourier. Can anybody tell me which one is preferably used for a frequency domain analysis? We are going to use a Laplace or we are going to use a Fourier transform? Can anybody tell me? Can anybody tell me for frequency domain analysis, what is preferred more? A Laplace transform is preferred more or a Fourier is preferred more? Okay, Deepak, if you are saying Laplace, can you tell me reason why we go for Laplace preferably over a Fourier? Why do we go for a Laplace transform over a Fourier transform? Why it is so? So I hope you remember at least. Let's say if there is f of t, and if I take a Laplace transform of f of t, I'm sure you know the formula. The formula is integrating over 0 to infinity f of t e to the power minus st dt, isn't it? This is the formula to have a Laplace transform of any signal which is a function of time, isn't it? And you know that after Laplace transform, obviously it becomes something called as f of s. This is something which is known to me. What is meant by S, guys? S is complex frequency. I repeat, S is a complex frequency, or in other words, I would say complex variable. When I say complex variable, guys, it will have a real part and imaginary part. So what I can write S as sigma plus j omega. So when S I say complex, sigma is what? It is a real part, and omega is what? Come on, it is called as an imaginary part. I hope you understand that. So wherever there is S, I'm going to replace with sigma plus j omega, because I know S value is what? It is sigma plus j omega. So let me write it. So below that, equal to, I would write 0 to infinity. I would say f of t e to the power minus sign I'll keep as it is. And in the place of S, I'll write sigma plus j omega t dt. Okay. So this is something which I have only substituted S equal to what? Sigma plus j omega. Nothing else, nothing great I have done. Okay, check it out. So when I integrate it over 0 to infinity, what I had in the previous page, I'll write it as it is f of t e to the power minus of sigma plus j omega we had t dt. So I can now describe this same as integration over 0 to infinity f of t. I can write this separately as e to the power minus sigma t e to the power minus j omega t. By law of indices, I can club them together, isn't it? I hope you understood that. Yes. Now listen to me very, very carefully, guys. Listen to me very, very carefully. There are two parts, guys. There are two exponential parts. Look at this and look at this. In these two parts, guys, in these two parts, which term is a frequency dependent? A first term is a frequency dependent or second term is a frequency dependent? Can you tell me? There are two terms, two exponential terms, first term and the second term. Which term you feel as a frequency dependent? A first term or a second term? Very simple question I asked. Which term you feel as a frequency dependent term? A first term or the second term? Very good. Second term, because second term has omega and first term there is no omega. So let me tell you, this is important. From what? From frequency domain analysis point of view. So second term is very, very important. So what is the significance of first term? First term gives you information. Obviously, first term will also give you some information. Second term will give you information regarding frequency. First term will give you information regarding transient part. Now, transient part is something called as an amplitude part. Okay. So this is something which is going to give me a transient part. So let me tell you clearly. Since my topic says it is a frequency domain analysis, I repeat, since my topic says it is a frequency domain analysis, there is no significance or no information required for transient. Only this much information is enough for me. First information I don't need. I don't want to get into transient analysis. I want to get into frequency domain analysis, guys, and that's the reason why I want to dump the first part. So how to dump the first part? By substituting sigma equal to 0, guys. By substituting sigma equal to 0. So what is going to happen? So this integration changes to 0 to infinity f of t. Obviously, when I substitute sigma equal to 0 here, it becomes e to the power 0, and e to the power 0 is what? Come on, 1. Anything next to 0 is 1. But the second term remains as it is, which is e to the power minus j omega t dt. Yes or no? And let me tell you, guys, this formula, I hope you remember, this formula is basically nothing but f of j omega, because this formula is nothing but a Fourier transform. I hope you remember Fourier transform formula. So this is nothing but a Fourier transform formula, guys. F of j omega. Yes or no? F of j omega. I hope at least you must have seen during your university exams, you substitute s equal to j omega. You substitute s equal to j omega. Come on, guys. What was the reason? What was the reason? If you remember, s is not j omega, guys. S is actually sigma plus j omega. S is actually sigma plus j omega. But I know that a sigma part gives me information regarding transient. Yes or no? And I don't want something called as transient, guys. I want something called as what? A frequency domain part only. That's the reason why you substitute sigma equal to 0. And the moment you substitute sigma equal to 0, the whole Laplace transform, because initially it was a Laplace transform, the whole Laplace transform gets converted into Fourier transform. That's the reason why for a frequency domain analysis, preferably we go for a Fourier transform and not for Laplace transform, guys. And that's the reason why you must have seen everywhere, even in Bode plot, even in polar plot or a Nyquist plot, you must have seen they do substitute s equal to j omega. They do not substitute s equal to sigma plus j omega. I hope these reasons are enough to make you aware why Fourier transform is preferred over a Laplace transform. Let me know, guys, have you understood my context? Have you understood that I have justified my statement that you have to use Fourier transform only and not as Laplace transform for frequency domain analysis? Guys, let me know. Okay, that's great. That's great. But I'm surprised that only Deepak is talking to me. Only Deepak is interacting to me. What about other people, guys? Come on, guys. You can also answer my questions. Okay. You can also answer my questions. You can also take a part in this live doubt session. Okay. So if you don't interact, then there is no meaning of taking live lectures, guys. So I hope you understood this. And with this, I believe that I must go ahead with some examples. Okay. So I'll start with some examples. And then it will definitely give you some confidence, guys. Okay. So the first question is, if the transfer function of system is y of s upon x of s, sorry, not x of s, we use r of s in control system. So let me use the same terminologies. Which is equal to s upon s plus 2. S upon s plus 2. Assume that this is a transfer function of a particular system. Okay. And input is simply cos 2t, then output is dash. This is the question which was asked in GATE 2016. This is the question from GATE 2016, okay? And some options were given. So I'm not interested to write options because output is something that we will definitely derive. So try to understand this kind of questions they do ask on this topic. Frequency domain analysis. Very, very important, guys. Similar questions are asked in even in signals and systems also. So this topic is something that you learn in signals and systems also. And this topic as a common part, you learn in control system also. So let's think from control system point of view. Again, this is a LTI system. This was provided in the question. This is a transfer function of a particular system, which is LTI system, for which the transfer function is known to me. Input is given to me. I have to get what is the output, guys. I have to get what is the output. Let us understand. Let us understand. Okay, so from basics we will understand. Don't worry, guys. From basics we will understand. I hope you are there. Stay tuned, guys. It is something important that I'm telling you. It might happen the similar question may get into your final exam and you may score 1 or 2 marks, okay, depending upon the complexity of the transfer function. Let's see. For example, if it is LTI system, guys, and if the input is a sine of omega t plus theta, assume that it is like that, then the output is a into m sine of omega t plus phi. Okay, let me say omega 1, then it would be omega 1 only. I hope you understood that. So let us understand what is meant by m here, because a is something which you will copy from here to here, no problem. What I'm interested to know, what is m? So let me tell you what is m. M is nothing but, see, let us assume if the transfer function is g of s. If the transfer function is g of s, just substitute s equal to j omega. Then common sense, it will become g of j omega. Then this will become g of j omega. What is g of s? Come on, it is nothing but transfer function, guys. It is nothing but transfer function. Then you will have something called a g omega with you. Yes or no? Yes. So magnitude is always mod of g of omega. Mod of g of j omega at omega equal to omega 1. What is omega 1? Omega 1 is something called as operating frequency. Okay, omega means omega equal to omega 1 means omega 1 is a operating frequency. This is how you can calculate magnitude. See, you can write it. You can just write it so that while solving the problem, you will have notes with you. And secondly, if you want to calculate this phi is nothing but, see, you have to consider old phi or old theta. So it is old theta plus angle of g of omega, where you have to again substitute omega equal to omega 1, where you have to substitute omega equal to omega 1, guys. This is how we calculate a new phi. Okay, this is how we calculating new phi. Okay, so our aim is to calculate first m and second what? Phase. Okay, once again, in LTI system, if the input is sine, output is also sine. Please try to understand. If input is sine, output is sine. Initially, what was an amplitude? Amplitude was A. What is a new amplitude? A into m. Out of which m is calculated by this formula. Next, if input is sine, output is sine. If the input is having frequency as omega 1, output is also having the same frequency. If the input was with a phase value as what? Theta. Okay, then output signal will have a phase equal to theta, that is nothing but the old phase, plus angle of g of omega at omega equal to omega 1. Okay, so I hope you understood that. Okay, so you have given an answer, and let me tell you, it is okay. Let us keep on the suspense. Okay, so this is a transfer function, guys. This is a transfer function. So transfer function given is what? It is s upon s plus 2. So very first step is what? Put substitute s equal to j omega, guys. Let us substitute s equal to j omega. Okay, don't worry. So it becomes g of j omega. It is g of j omega equal to what? J omega upon j omega plus 2. So I got g of j omega. Yes or no? See, if you remember our LTI system, in our case, the input given is cos of 2t, guys. Cos of 2t, isn't it? Then the output is, you know very well, the output is something called as, see here, as you can see, a equal to 1. As you can see, a equal to 1. And if you compare with the standard form, guys, phi equal to 0. Sorry, theta, not phi, but theta equal to 0. Your theta equal to 0 degree. Yes or no? Because we know that the in general form I can write a cos of omega t plus theta. I hope you understand that. Yes or no? And again, very good, Malish. You are 100% right. Very good. What you have calculated is now correct. So next, if you want to get omega, then compare omega with this coefficient of t, which is 2. So omega equal to 2. So these things I have come to know looking at the input. Now I'm interested to calculate what output. So I know what is my output, guys. My output is something called as am cos of omega t. In fact, omega is equal to 2, so I would write 2t only. Omega 2t plus what? Phi. So my aim is to calculate what? M and phi, because a is 1. A is 1. I know that. So how to get m? Very simple. M is what? It is mod of g of omega, which is nothing but mod of j omega upon j omega plus 2. Yes or no? See, mod means what? Magnitude. Mod means magnitude. What is the magnitude of j omega? Simple, omega. What is the magnitude of j omega plus 2? Simple, under root of real part square plus imaginary part square. So it becomes 4 plus omega square. So this becomes the magnitude, guys. This becomes a magnitude. I hope you understood the magnitude, guys. I hope you understood the magnitude. Let me tell you, guys. Let me tell you very clearly. This magnitude you calculate at omega equal to operating frequency. What is the operating frequency, guys? 2. Then just substitute omega equal to 2 in this m expression. So m becomes ultimately what? Come on, guys. 2 upon, okay, 2 square plus 4. Okay, 2 square plus 4 means it is under root 8. Yes or no? It is under root 8. So if you calculate, you'll get m equal to what? 1 by root 2. This is equal to what? 1 by root 2, guys. So I hope you understood this, how m is equal to 1 by root 2. Okay, very simple, very simple. Okay, so next, if I want to calculate phase, guys, if I want to calculate phase, how do we calculate phase? Phase is equal to original theta plus angle of j omega at omega equal to what? Okay, operating frequency. At omega equal to what? Operating frequency, whatever operating frequency is given. So in this case, if you remember, theta is equal to 0 degree. In this case, theta equal to what? 0 degree, guys. Since theta equal to 0 degree, let me substitute theta equal to 0 only. Plus, I have to take angle of g of omega. So what was g of omega, guys? G of j omega is this, j omega upon j omega plus 2. So let me take an angle of this. Sorry. So whenever you are taking angle of, remember, a by b, then it is always angle of a minus angle of b. Remember that. So when it is angle of a by b, it is always angle of a minus angle of b. So with that, I can write it is equal to angle of j omega minus angle of what? J omega by 2. Sorry, j omega plus 2. Yes or no? What is angle of j omega? If you calculate, you will get 90 degree. What is angle of j omega by 2? Very simple. It is tan inverse of imaginary part upon real part, that is omega by 2. But let me tell you, guys, omega equal to 2 radians per second, if you remember. Meaning that this becomes tan inverse of 2 by 2. Tan inverse of 1. Tan inverse of 1 is what? It is 45 degree. 90 minus 45. Phi becomes what? 45 degree. Very simple, guys. So with this now I have calculated what? Phi also. So now if my input to LTI system, if my input was LTI system was what? It was cos of 2t. Then my output is what? First of all, you have to write what? A into m. A is equal to what? A is equal to 1. And if you remember, m was equal to 1 by root 2. Let us check. M is 1 by root 2, guys. So it becomes 1 by root 2 cos of 2t. Okay. plus what? The angle is 45 degree. So this is your output, guys. This is your output, guys. I hope everybody has understood how to get the output for a sinusoidal function. Okay. So what I'll do, I'll just change the problem. Okay. And I'll ask you to now calculate what is the output for a given sinusoidal input. So I'm going to change the sinusoidal input. Again, assume some LTI system. So question number 2, I'm going to start with, guys. Okay, both of them are gate questions only. So previously it was, previously it was gate 2016 problem from electrical branch. Now this is again gate 2016 problem only, but from instrumentation branch. Okay. So again, this is gate 2016 problem, guys. So now assume that the input is 2 sine of 3t plus pi. This time the input is 2 sine 3t plus pi. And now this is applied to LTI system having transfer function as, okay, having transfer function as 8 upon s plus 8 the whole square. Okay, s plus, sorry, not 8, it is 10. Let me correct it. Let us not change the data so that we can verify with answers also. Okay, so it is s plus 10 the whole square. If this is the transfer function, then you have to get what is the output. You have to get what is the output, guys. Again the same thing. Again the same thing. Come on, guys. G of s is known to me, guys. G of s is known to me. Okay, so those who know how to calculate it, start doing that. Okay, so this is something called as transfer function, that is g of s, function of s. So let us substitute s equal to j omega in order to get what? G of j omega. So what will be g of j omega? Very simple. So wherever there is s, replace with j omega. So it will become 8 upon j omega plus 10 whole square. So this has become g of j omega, guys. This has become g of j omega. Yes or no? Very simple. Next, what you have to calculate? Come on, guys. If the input is 2 sine 3t plus pi, okay, guess what is the output? Guess what is the output? Output will be like this. Okay, if you remember, it is a into m, but this time a is what? 2. So it will be 2 into m sine of, because if the input is sine, output is sine. If the input was cos, output was cos. So with the same context, omega is 3, it remains same. Plus, come on, you have to consider this pi. Plus what? Plus 5. So now you have to calculate what? You have to calculate m and you have to calculate 5. Very simple. Very simple. So let us calculate. Let us calculate m here. Let us calculate m here. What is m? Come on, m is nothing but mod of g of j omega at omega equal to operating frequency. What is the operating frequency? It is coefficient of t, which is 3. So omega equal to 3, guys. Omega equal to 3. Let us do that. Let us do that. So you have to get the magnitude of 8 upon j omega plus 10 whole square, isn't it? So obviously, when it is magnitude of numerator upon denominator, it is magnitude of numerator divided by magnitude of denominator. So magnitude of 8 remains 8, obviously. Don't think about square now. Okay, think about only j omega plus 10. So if it is a plus jb, what is the magnitude? Root over a square plus b square, that is real part square plus imaginary part square. So I'm doing the same. I'm doing the same. It is, under root of omega square plus real part square is 100. Okay, and since it was square, so I'll take a square of that. I hope you understood that. In that case, guys, in that case, let me tell you, square and under root will cancel each other. Square and under root will cancel each other. And at the end, guys, you will have magnitude equal to what? 8 upon omega square plus 100. But you know what? Omega is something which is 3. If you remember, omega was equal to 3. So substitute omega equal to 3. 3 square becomes what? 9. So ultimately, m becomes what? 8 upon 109. So the value of m has come, guys. The value of m has come, which is 8 upon 109. 8 upon 109. So here you will be substituting 8 as, m as 8 upon 109. 8 upon 109 multiplied by 2. Okay. So, okay, let me see. Okay, Malesh, you made a bit mistake there, a bit mistake. Okay, I'll tell you what it is. Okay, no problem, no problem, Malesh. I'll tell you what is the mistake. Okay, so I hope the magnitude that you have got it same. That is 2 multiplied by 8 upon 109. Okay, only phase part we need to clarify. Deepak, I hope you are there. Deepak, I hope you are there. Okay, so let me see what is the phase that you are supposed to get. So what is phase? Phase is simply, you know, uh, it is original theta. It is original theta plus angle of g omega at omega equal to 3, because operating frequency is 3. So great. So theta is pi. If you remember original theta, it was pi. So I have taken pi plus angle of g omega. So you know what g of j omega is known to me. So when I say angle of g of omega, it is angle of 8 upon angle of this. I hope you understand that. So it is angle of 8 upon angle of what? J omega. Okay. J omega plus 10. I can write j omega plus 10 whole square as j omega plus 8. Sorry, j omega plus 10 into j omega plus 10. So eventually I can write it is angle of like this. Because j omega plus 10 whole square, I can write it as twice j omega into 10, j omega plus 10 into j omega plus 10. So I have ultimately did the same. Okay. So it is pi plus angle of 8. Obviously it is 0 degree. So it is 0 divided by angle of j of omega plus 10. It is obviously tan inverse of imaginary part upon real part, guys. Imaginary is omega, real part is 10. So omega by 10 plus, again it will be same, that is tan inverse of what? Omega by 10. And obviously it will be what? Pi. Okay, so this will be 0 minus 2 tan inverse of the angle. Okay, so it is minus 2 tan inverse of omega by 10. Omega by 10. So this ultimately becomes pi minus 2 tan inverse of, what is omega, guys? It is 3 by 10. 3 by 10 means what? It is 0.3. 3 by 10 is what? It is 0.3. So let me just go ahead. Let me just go ahead for writing the phi. So phi is what we have written, pi minus 2 tan inverse of 0.3. Can anybody tell me what is the answer for this? Deepak, Malesh, can you tell me what is the answer for this? 2 tan inverse of 0.3. You can use your calculator and let me know. So what you get is 33.39. This is 33.39, guys. 33.39. Okay. Try to understand this 33.39 is in degrees. 33.39 is in degrees. And if you look at this pi, guys, this pi is in what? It is in radian, guys. It is in what? Radian. So obviously you cannot do that. If the unit of pi is radian, if the unit of this is in degrees, you cannot do any calculation. You cannot do any calculation. So rather what you can do, you can just substitute, pi as what? Pi as what? 180 degree. You can substitute pi as 180 degree. And now you can say it is 180 minus what? 33.39 degree. Yes or no? So if you do so, you will get 146.60 degree. You'll get 146.60 degree, guys. Okay. So in this case, now the final answer becomes what? Come on. It is 2 into, it is 2 into 8 upon 109. Okay. Sine of 3t. Okay, 3t plus 146.60 degree. So this becomes the final answer, guys. This becomes the final answer. I hope you are getting what I tried to explain you. Okay. try to remember, this is something that you will also come across in the GATE exam, that this is in radian, this is by default in degrees, because the virtual calculator that you are using, okay, virtual calculator, I'm sure you are using a virtual calculator. In that case, you will always by default get the answers in degrees, and radian and pi you cannot club together. So either you calculate radian to degree or degree to radian and then only club it together. So this is how the care should be taken, guys. I'm sure you have enjoyed this lecture. I'm sure I could add something to your existing knowledge. And it was beautiful to teach you guys. If you interact with me, then it is, you know, it becomes very easy for me to analyze whether you are understanding or not. Thank you so much for attending, guys. Keep attending my lectures. I take control system every week on the same time, and not only control system, but other than control system, I take signals and systems. Okay, I teach digital circuits also. So stay tuned to Ekeeda, guys. Keep subscribing the channel. Tell your friends, even for subscribing this channel, so they will also get benefited. Thank you so much, guys. Uh, Myself, Professor Abhishek Barve, I sign out today. Thank you. Deepak, can you tell me what was the question? See, that is the property of LTI system, Deepak. The same I have explained when you asked me. Let us say you have a sine of, omega t. Okay, if this is the input, and if you give it to LTI system, if you give to LTI system, because of its time invariance property, it, if you give sinusoidal input, you get sinusoidal output only. Okay, then if the frequency is omega, then here even the frequency is omega only. What only changes in LTI system, guys? This amplitude. This amplitude changes to another, that is a into m. And what changes is the phase. So you get a new phase. So try to understand, in LTI system, only amplitude and only phase changes for a sinusoids input. That is the behavior of LTI system, guys. Okay, that is the behavior of LTI system. M means what? It is gain. It is gain provided by the system. Okay, so to existing amplitude, you are multiplying by m, where m is the gain which is provided by that LTI system. I hope you understand that. And phi is something which is phase, which is added to the system. Okay, sorry, not to the system, but to the existing input. It is added and the output is calculated. So thank you so much, Deepak, for staying connected, and see you in the next lecture. Thank you. Bye bye. Take care. Good night.